So in chapter 4, we'll go over all the concepts we have learned, and we'll generalize them in terms of vector spaces. So let us discuss the definitions and examples about the vector space in this section. So the vector space is a set of vectors V with two different operations called addition and scalar multiplication, and they should satisfy the following 10 axioms below. So if I divide this into two parts, then the first 5 is about the vector addition, and the other 5 are about the scalar multiplication. So indeed, you can tell that, well, these were algebraic properties of vectors that we have seen in section 1.3. But in this time, you're going to declare a set is the vector space as long as that satisfies the following 10 conditions. And we can deduce these 3 facts by using the above definitions. So for example, for the first one, we know that 0 equals to 0 plus 0. But if you multiply u for the both sides, then we get 0 times u equals to 0 plus 0 times u. Or if you distribute this, then we get 0u plus 0u. And if you cancel out 0u for the both sides, then we get 0u equals to the 0 vector. And if you use the similar argument like this, you can prove c times the 0 vector equals to the 0 vector, and the additive inverse of the given vector u equals to the -1 times the vector u. So let's see some examples of the vector spaces. R to the n, which is the set of n-dimensional vectors, and this is indeed a vector space when the vector addition and scalar multiplications are defined component-wisely, and we have checked that R to the n satisfies the axioms for the vector space in chapter 1.3. And moreover, consider a set of m by n matrices for m n fixed. And we know that the matrix addition and scalar multiplication are defined component-wisely, and the zero matrix is the matrix consisting of 0 entries. And we have checked that the set of matrices satisfies the vector space axioms in section 2.1. Okay, so consider the set S to be the set of doubly infinite sequence of numbers. So which means the element of S is given by y sub k, where y sub k is a sequence that goes all the way to both right and the left direction. So let's take two different elements, y sub k and say w sub k, that is given by w sub -2, w sub -1, w sub 0, w sub 1, and w sub 2, and so on. And if you set u, the vector u equals to this one, and w equals to that one, then how would you define u plus v? Well, we can define u plus v as y sub -2 plus w sub -2, comma y sub -1 plus w sub -1, comma y sub 0 plus w sub 0, and so on. And we can also define the scalar multiplication by c times y sub -2, c times y sub -1, and so on. So note that we define the vector addition and scalar multiplication component-wisely. So checking the vector axiom is equivalent to checking the axioms for R to the n, the usual Euclidean vector space. So this tells you that the given space S is a vector space. And if you plot an element in S where the entry number goes to the x-axis, the value of the entry goes to y-axis, then we can regard that element as the discrete time signals. So if you go to the next page, we have a nice picture for that. So for example, this point corresponds to y sub 10, and that point corresponds to y sub -10. And if you identify all the points with entries of the vector, then we can tell that the vector represents the discrete time signal. Here's another non-trivial example for the vector space. So suppose that P sub n to be a set of polynomials of degree at most n, or the degree less than or equals to n. Then we can define addition and scalar multiplication in a natural way. That is, if you take two different elements, so say P of t and Q of t, where Q of t is given by B sub 0 plus B sub 1 t plus so on until B sub n t to the n, then we can add P of t and Q of t by adding the function value of the given polynomials. That gives you a sub 0 plus b sub 0 plus a sub 1 plus b sub 1 t, and so on until a sub n plus b sub n times t to the n. And the scalar multiplication can be defined as the usual multiplication, like c times a naught plus a sub 1t plus so on plus a sub n t to the n, which gives you ca0 plus ca1 t plus ca sub n t to the n. Okay, so we defined a vector addition and scalar multiplication. So let's pause the video and check whether the given space satisfies the 10 axioms for the vector space. Okay, so let's solve this problem together. So I copied all the axioms below. So the first thing we have to check is whether the space is closed under addition, which means P of t plus Q of t has to be an element of the given space P sub n. So we know that adding two polynomials does not increase the degree of the polynomial. So P of t plus Q of t is a polynomial of degree less than or equals to n. And this implies that P of t plus Q of t belongs to our space P sub n. And second, note that we define the addition as the usual addition in the real line. So we know that the addition satisfies the commutativity and associativity. And if you define the zero vector as a zero polynomial, which is given by f of t equals to 0, then that gives you 0 plus p of t equals to simply p of t. And we have the additive inverse in p sub n, which is precisely given by negative p of t. And also for the multiplication, multiplying scalar does not change the degree of the polynomial. So it is again a polynomial of degree less than or equals to n, which means c times p of t is an element in p sub n. And again, we define the multiplication similar to the multiplication of the real numbers. So that tells you all the axioms from 7 to 10 is true in this case. Let me give you one non-example for the vector space. So suppose that R sub bigger than or equals to 0 to be set of our numbers such that x is non-negative. This corresponds to half real line that consists of positive numbers. And this set is not a vector space. And can you tell the reason why? Well, this is because the set does not have any additive inverses. Or for example, like if you take 2 from the set, then the additive inverse for 2 should be negative 2. That does not belong to R sub greater than equals to 0. Okay, so let's consider a set of real valued function defined on the domain D. Then we can write this set as like the set of all functions f, such that f maps D to R, where D is a subset of R, or we can simply write D is a subset of R. Then for example, a vector in this case, well, if D is set of all numbers which is greater than 0, then like the log of t is an element in this set, and 1 over t is also a real valued function So if you have two different functions like this, then how would you add these functions? Well, we can add their function values to define the addition, which means f plus g of t can be defined as f of t plus g of t, and the scalar multiplication cf of t can be defined as multiplying c to each function value. Then you can check that the space V satisfies all that axioms for the vector space. So you want to pause the video again and verify whether it really satisfies the axioms. So if you write all the axioms like this, then you can immediately tell that the given space satisfies all the conditions, because we define the addition and multiplication similar to those in the real numbers. But here the zero vector corresponds to the zero function, which is defined by 0 of t equals to simply 0. So if you plot these functions, then we can visualize them as a graph over their domains. So a subspace is a space H that sits inside the original space V, or it is a vector space that lives inside a bigger vector space, and it should satisfy the following three conditions. So first of all, H should contain the zero vector of V, and H has to be closed under addition, and H has to be closed under scalar multiplication. So there are 4 fun exercises below about subspaces, and you want to pause the video and think about those 4 questions before I give you the solutions. So let's begin with the first problem. All the vector spaces have at least one subspace, right? Which is given by zero vector space. Indeed, it contains zero vector, and it is closed under addition. And whatever you multiply any number, say like 777 into 0, which will still give you 0 as well. So the zero vector space is always the subspace for any vector spaces. How about part B? So first of all, we know that polynomials are functions from R to R. So we can tell that P is a subset of, so let us say the vector space of all functions to be F, then it is a subset of F. And we know that 0, the zero function belongs to the polynomial because 0 is the polynomial. And if you add two different polynomials, then you still get polynomial. And even though you multiply some number into a polynomial, then it is still a polynomial. So we can tell that the set of polynomials is a subspace of the vector space of all functions. And how about C? Well, it looks like so, but note that R squared or R2 is not even a subset of R3. And this is because R2 has 2 entries, but R3 has 3 different entries. Okay, so for part D, if the plane does not pass through the origin, then for example, if you consider a plane which is given by z equals to 1, then we can plot this into here, right? And it doesn't pass through the origin. So if you say this to be h, then 0, 1, 1, and 1, 0, 1 are elements of h. But if you add these two elements together, then this gives you 1, 1, 2 that does not belong to the given set H. That tells you the set H is not closed under addition. Okay, so let's consider the case when the plane passes through the origin. So for example, if H equals to x, y, and 0, then in this case, we get H is a subspace of R3, and this is because we have the 0 element, the 0 vector, sits inside H, and if you take two different vectors from H, say x1, y1, and 0 plus x2, y2, and 0. And this gives you x1 plus x2, y1 plus y2, and 0. That again belongs to H. And if you multiply some number into x, y, and 0, then this gives you cx, cy, and 0. That again belongs to the given set H. So if you plot that H into three-dimensional space, then we get a plane that looks like R2, looking like this. And in this case, we say a subspace H is isomorphic to R2. Or in other words, that means H looks like and acts like R2. Now, a linear combination of vectors is given by this, which is very similar to what we did in chapter 1. And span of these vectors are given by all possible linear combinations of these vectors. So basically, if you take two vectors, v1 and v2 from V, and if you let H to be span of these two vectors, then H forms a subspace of the given vector space. And this is because, so basically we have to check whether 0 sits inside H, and whether H is closed under addition. So if you take two different elements from H, then x plus y should sit inside H, and we have to show H is closed under scalar addition. Okay, so first of all, the 0 vector is indeed sit inside H, and this is because we can write 0 as 0 times v1 plus 0 times v2, which means 0 is a linear combination of v1 and v2. So this tells you 0 sits inside the span of v1 and v2. Second, if you take any element x and y inside the span of v1 and v2, then we can write x as a linear combination of v1 and v2, and y as the linear combination of v1 and v2 as well. Then if you add x and y together, then this gives you c1 v1 plus c2 v2 plus d1 v1 plus d2 v2, or that gives you c1 plus d1 times v1 plus d2 plus d2 times v2. And again, x plus y is a linear combination of v1 and v2. It is an element of the given space H. Lastly, if you take x inside the span of v1 and v2 and write x as, say, a v1 plus b v2, then c times x gives you c a v1 plus b v2. That gives you ca v1 plus c b v2. And again, it is a linear combination of v1 and v2. Equivalently, cx is an element of H. So for these reasons, H, which is a span of v1 and v2, is a subspace of the given vector space V. So we can generalize this to p number of vectors. So suppose that V is a vector space and v1 to vp's are element of V, then span of this element is always a subspace of V. So in this case, we call the span of this set as the subspace spanned by the set of element v1 through vp. Okay, so using the theorem 3 above, let's prove that H is a subspace of R4. So basically, we can observe that a general element of H, which is given by a minus 3b, b minus a, and b, can be split into two different parts. So for example, a minus a, and 0, plus negative 3b, b, 0, and b. So I separated each variables. Then this gives you a times 1, negative 1, A0 plus B times negative 3, 1, 0, 1. So from here, we can tell that an element of H is a linear combination of these two vectors. Or equivalently, H equals to span of these two vectors. And by theorem 3 above, we can conclude that H is a subspace of R4. Okay, so using this fact, we can identify all the subspaces of R3. So basically, we know that the zero vector space is always the subspace of any vector space. And if you begin with a single vector V, then the subspace should be closed under addition and multiplication, which means C times V's are always elements of the subspace. So span of V is a subspace of R3, and this corresponds to a line passing through origin. And if you increase the dimension, or if you begin with two linearly independent vectors, then this gives you a plane passing through the origin. And if you increase the dimension again, you will get whole space R3 as a subspace of itself.